disturbing picture. But now we're going to be putting the balls in the head to make things publicly verifiable. Okay, so I'll start by telling a little bit the story of, I guess, how this happened, and show a little bit the connection with MPC in the head, which maybe isn't immediately apparent, but perhaps we'll see a little bit later. So our goal was to get something like these nice and simple, efficient VOLE-ZK proof systems, which we saw in the last lecture, in the designated verifier setting, and make it public domain so that you can have something where you can apply fiat Shamir and get a non-interactive zero-knowledge proof. Okay. And we kind of drew inspiration from two angles. So on the one side, MPC in the head-based protocols and KKW, a bit like what Carsten talked about. And then on the other hand, using techniques more from multi-party computation, like OT extension and homomorphic commitments, which were kind of designed in different settings. But putting these things together kind of led to this VOLE-in-the-Head approach, which then we realized was actually, something like a publicly verifiable version of the original VOLE-ZK. But in parallel to this, there's been another line of work purely on MPC in the head. That's developed some techniques like the hypercube technique and this threshold computation in the head approach, which actually use very similar techniques to what we use in VOLE-in-the-Head. You can kind of see this as a generalization of this, although not exactly. So yeah, these things are very closely related. But I think VOLE-in-the-Head, maybe I'm a little bit biased, but I think it encompasses everything you need to know, and you also don't need to know too much about the MPC in the head-based background to understand it. Okay, so I'll start with a quick recap of MPC in the head. And the high-level structure of this, something like this KKW protocol, where we have n parties and n views, of which n-1 are revealed to the verifier. So remember, the prover always starts by secret sharing the witness W into these shares, and then generating the views, which are committed to and opened after a challenge from the verifier. So in our case, now we're going to think of W as not just the input to the circuit that's being verified, but also this extended witness, so potentially also some outputs of multiplication gates or whatever, just like we had in the VOLE protocol. And now, instead of doing MPC in the head, now Alice is going to basically generate some voles, which commit her to the witness, but now kind of in the head, and generate a kind of commitment to the verifier, which commits it to these inputs to the voles, such that later we can get a public challenge from the verifier, which is going to play the role of this delta, and will allow Bob to learn this output of the VOLE correlation, so the Q, which is just the evaluations of these two lines at the point delta, and then can verify the proof. So we're not exactly going to be using a VOLE functionality. We're using a kind of public variant where now this challenge delta from Bob may be leaked to the prover. So we have to be careful how we do this to make sure it works. And the connection to MPC in the head is that this delta will also define the sets of shares of the witness, which is secret shared in the beginning, and the subset of n-1 of these, which are opened. So the magic is kind of how to translate the secret sharing into this VOLE, so that now you can get away with simply doing a VOLE-based proof instead of this more complicated entire multi-party transcript of an MPC protocol. Okay.
Send to check. So the delta, once again, the delta is publicly visible or not?
This time the delta is public.
And the protocol will be publicly verifiable, right? Yeah. Okay.
Yeah. So to kind of maybe capture this a bit more formally, you can think of a relaxation of the VOLE functionality, which kind of captures VOLE in the head, or what I call public receiver VOLE. So where the output of Bob, or the input of Bob, is this delta value, which may be leaked to the corrupt proof. Okay, so we still have privacy on Alice's side for her V and W vectors, and we think of this as a two-stage protocol where first Alice will be committing to the V and W vectors, and then later Bob chooses the delta, and Alice may learn the delta. Okay, so it's clear if you have a standard secret VOLE protocol, then you can just implement that and then you satisfy this functionality. You just have less leakage. But the hope is that we can actually do something that's a public coin protocol by relaxing the security requirement. Okay, and what we use for this is exactly this all but one vector commitment, or GGM trees, which Carsten talked about, which gives us a nice succinct way of committing to these, say, n sets of vectors or n secret shares of a witness, such that later we can open all but one of these with only logarithmic communication using this tree-based approach. Okay, and the challenge delta just defines the entry of this set of vectors, which we don't open, so that both. Okay, and what we need now is some kind of magic procedure to take these sets of shares, so all n shares on one side and n-1 shares on the other side, and use them to define a VOLE correlation, which is going to be of a some finite field where Bob can define some evaluation of vectors at the point delta. Okay, so how can this work? So let's look at this a bit more concretely. So Alice commits to the WIs, and now we're going to view each of these vectors as a vector over the finite field with n elements, where n is the number of shares that Alice commits to. Okay, and then the delta challenge is, of course, a challenge of between 1 and n, so we can also view it as a finite field element. Okay, we open n-1 of these, and now viewing these all over this finite field. So, okay, Alice can define her witness, which is the sum of these n shares over the field. She can also define this v vector by taking a linear combination of the field of the n vectors, multiplying with elements 1 up to n. And now Bob can take a similar linear combination by defining the sum of the WIs that it receives, but now multiplied by delta minus I. So now remember, Bob doesn't have W at index delta, but then delta minus I is 0. So that doesn't matter. Bob can compute the whole of this sum. And this is equal to W times delta plus this V term, which Alice computed.
It seems the prover doesn't really care about the delta. Is that the point? Or
yeah, so in the beginning, the prover doesn't need to know delta, and it can compute W and V, right? This is already after the commitment phase. And then later on, when we want to, Bob to learn the output, Bob can send delta. You can open these, and Bob can get the Q. Alice was already committed to the W and the V from the beginning. Yeah. So intuitively, if we want to use this for zero knowledge, well, since delta will be revealed, we can't really do anything related to the the previous VOLE-based commitments we were using or those zero knowledge protocols once delta has been revealed. So the way it's going to work is we first have this commitment phase, then we have Alice send all of the multiplication checks or whatever else in the proof, and then at the very end we have the delta challenge. Open this and have Bob check the outputs. Okay, so just to recap what we get from this public receiver VOLE. So it's a way of creating this VOLE correlation, which suppose for now that the W's are just random or pseudo-random, then actually the communication in this, because of the tree optimization, is only logarithmic in the length of the vector. So you have to send log n seeds to open these commitments. And the computational cost for both the prover and the verifier is, of course, linear in the field size and the length of the vector. So this field size n we have has to be small.
Is that where the GGM tree is relevant?
Yeah, the log n seeds. Yeah.
where does it come on the previous slide again? The tree?
The tree, I guess it wasn't on this slide, but so the commit to the WI,
Oh, here is
that's committing to the
tree.
the leaves of the tree.
Commit to the root of yeah.
Yeah, and then the opening is sending
Okay.
the paths, the log n paths. Yeah. So if W, all the shares are random, then this only needs logarithmic end communication. If W, needs to be chosen related to the witness, then okay, you just send, proportionally extra field elements to correct the random ones into chosen ones. Okay, so it gets you kind of a vol output over a small field of size n, but with like optimal communication. Well, maybe not optimal, but like great. Okay, so then with that, the zero knowledge protocol, or at least the simplest flavor of the zero knowledge protocol, just has a simple 3-round structure. So Alice starts by doing these commitments to the tree, and then runs this vol conversion procedure to learn the vol vectors, the W and the V, and sends the multiplication checks along with the first message. This is exactly the proof we had in the basic non-interactive vol-zk protocol in the last part. Then Bob sends the delta challenge. Alice opened these using the GGM tree openings. And Bob uses this to define his Q values and learn the results. Okay, so yeah.
So this depends on like the multiplication checks essentially being committed.
Yeah, so Alice can compute these already without the delta being defined.
One thing, but the field can also be larger than n, right? It just should not be smaller than n.
Yeah. So if the field is larger than n, then the delta is just like chosen from a subset of size n. So the soundness will always be 2 divided by n. So the field may be larger if you want. Yeah.
How does the soundness attack here works?
What do you mean by attack?
Well, but
The argument for two.
the argument of why is 2 over n, and what happens with how do the prober can cheat?
Right. So it's the same as the multiplication checks in the previous lecture. Right. So you have these degree 2 polynomials.
Okay, I see.
Yep. And these multiplication checks you're sending over. And if any of the multiplication gates is incorrect, then one of these
You just need to get one gate incorrect. Right?
2 polynomials or error polynomials must be non-zero.
Okay.
But it should evaluate to 0 at delta.
Okay.
Yeah, the verify and then he computes a single Q or
So he gets a vector of Qs. The single Q vector.
yeah.
And then uses it to define all the multiplication formulas.
So we're still working on the small field, and this is why they are so basically okay.
Yeah.
Schwarze pullover, like
It's not sure it's a little bit small. Okay. Yeah. So of course, to boost the soundness error, you can do parallel repetition. This is an honest verifier Sigma protocol, so that's fine. Maybe a quick note that so even if the field is like somewhat large, if you want to do say a proof of a Boolean circuit, then you can actually get away when you commit to these WIs by only sending commitments corresponding to 1 bit of the field element by working a characteristic 2 field. You have to play around a little bit with how the trees are defined, but then this communication can essentially be like 1 bit per bit of the witness in the multiplication gate. Plus the repetitions, of course. So now we're gonna build up a little bit to the what I think of as the full VOLE-in-the-Head protocol, which adds a couple more optimizations. So the first one we already saw in the last time, it was just batching the multiplication checks. Okay, so get a random challenge, send over a single randomized polynomial instead of all the multiplication polynomials, which makes this soundness error. Actually, that's not quite right, but yeah.
This random challenge they use to combine all the polynomials, that can be taken from an extension field, right?
Yes.
That doesn't need to be
Yes.
from the tiny field.
Yes, it can be. Yeah, and that helps. This. But it's not 3 of n. That should be like 2 plus the number of multiplications. So this gets us the 5-round Sigma protocol, which we can also do parallel repetition of and apply Fiat-Shamir to. But if you're familiar with Fiat-Shamir and multi-round protocols, then we have a bit of an annoying problem here, and that the soundness doesn't quite go as small as you'd hope. Because there can be kind of weird attacks where you can maybe attack different rounds of the protocol in different parts and then try to reduce the soundness after you've applied fiat Shamir in a better attack than what you'd expect, looking at the soundness of the interactive protocol. So yeah, to get around this, we have a solution where we add more rounds, but actually the goal of this solution is to turn it into a protocol that isn't just purely parallel repetition based. It's kind of everything happens all together. So you don't have these attacks which rely on being able to attack different executions in different rounds, which somewhat breaks fiat Shamir. So what we do is, instead of just naively repeating this, say, tau times, where we create tau sets of voles and then run tau multiplication checks for each of these, we're going to kind of pack all of these tau voles into one big extension field. Okay, and then run one big vol check over the extension field. Okay, so imagine the original field we work in, it's over FQ. And then we have tau repetitions. So now we're going to lift these into the FQ to the tau extension field. So for instance, if we let alpha be some generator of the base field of the extension field, then you can take all of the verified delta right challenges and lift them like this into the big field. And then do the same thing for the provers vectors, so the V and the W, and end up with a single vol correlation over the extension field. Which means once we've done this, okay, we still have to do tau vols in the first place, but then the actual zero knowledge part, the multiplication checks, just need to be done once over the big field. It seems like this maybe helps, but it's not quite enough. So now we have a problem that the prover might use different W vectors in each of the tau vols we start with. And then when we combine these into the big fields, we're kind of messing things up. And actually doesn't quite work out as good as you want. And there might be things that can go wrong and your soundness still isn't quite good as good as what you hope. And this is where the extra round comes in. So now we add a consistency check, which we take from this soft-spoken OT extension protocol, which kind of uses similar ideas to build oblivious transfer, where the receiver will sample a random challenge. In this case, it could just be some random field elements. So now we'll define it to be a linear universal hash function, basically a structured randomized matrix. And then you hash all of the vector relief vectors in each of the tau repetitions down to a single smaller vector and send these over to the verifier, who will check that the hashed linear relation also applies on the Q outputs that it receives. And at a high level, this makes sure that this W vector that Alice is supposed to use in each of the tau iterations is consistently the same one across the tau different voles. But the analysis of this is actually quite tricky, and especially you want to prove that this is compatible with fiat Shamir.
You've been using the color red to indicate secret values, right?
So it's more like, I guess it was secret values, now it's just values chosen by the verifier.
So the hash function is chosen by the verifier.
Yes. Yes. So now it's public coin, so there's not really any more secret values verified.
The actual soundness reflect mentioning tau or was.
So for this part, I mean, it depends on the hash function. So it basically it's roughly as big as the output of the hash function. So if this outputs lambda bits, you have 2 to the minus lambda, maybe plus some like tau squared factor. There's a bit of a loss in tau. Yep.
If we just agree on a set of security properties for the hash function, would it necessarily still be something that we sort of like rely on the verifier to choose? Can't it just be specified?
Right. So it's the properties required. It's sampled at random from a family of universal hashes. So it's not like a cryptographic hash function you normally think of.
A family of universal hashes.
Yes. Yes. So think of it as a family of matrices. You pick a random matrix in this family, and then send over that matrix.
That's super different from what I thought.
Yeah, yes. I think if you're not familiar with universal hashes, maybe it's a little confusing. Yep.
Have an embedded key or something like that, which has
I guess the matrix you select from the family, you can think of as the key for the hash. Yeah. But just think of it as, you can also think of a simpler version where you just send some random challenge which defines a linear function that the verifier, the prover applies. Okay, so then we have the complete VOLE-in-the-Head protocol, at least over small fields or over F2, which now is this 7-run protocol where the verifier sends 3 challenges. So first of these to check the multiplications and batch them together. The second to check that the vectorials are consistent. And then the third one to actually choose this challenge delta and then send the openings of all of the EGM trees that were committed in the first round. Okay, and at least this version, if you run it over F2, when choosing parameters for say 128-bit security, the concrete proof size cost works out to around 10 to 16 bits per AND gate. So this is roughly the number of repetitions you do in the protocol. Or if you work over large fields, then you can work a little bit harder to avoid these tau repetitions coming into play. And then end up with something which just has an overhead of around 1 or 2 field elements per multiplication gate.
How large is large here?
As big as your security parameter.
Okay.
2 to the security parameter. It's 128-bit.
But this is an extension field, right? It's not.
It could be a prime field.
Okay. Yeah. How does the VOLE work over that? Like the VOLE in the head? Like because there the computation is proportional to the characteristic.
Yeah. So then you have to choose the delta to be from a small subset.
Oh, okay. Yeah.
But then to boost the soundness, instead of doing kind of more repetitions, you use error correcting codes.
Okay.
A bit like Ligero.
But this, like, once you go to prime fields, things are a huge pain.
That sounds like
We are happy to explain it offline.
Yeah. But the huge pain can be quite beneficial. if
Yeah,
you're
yeah.
Prepared to work. Yeah. And I think, yeah, that's all I wanted to say about VOLE in the head. I don't know if anyone has more questions about that, or I'll move on to the second part about signatures.
One more question, which I'm not sure if I answered correctly. So the original VOLE, we had this designated verifier. It was just part of the definition how it works, that we don't want the one party to learn what this delta is.
Yeah.
But it was not really with zero knowledge in mind. We kind of, not like we destroy soundness or something. If we remove this, it's
Yeah.
basically just really if it's like this and okay.
Yeah, so all the, the VOLE zero knowledge protocols, they work with this relaxed version of the function.
Okay.
That's kind of,
Yeah, I got the correct takeaway.
I guess one thing you're maybe losing here is that now you have to do your proof all at once. Right? So I can't say do one part of the proof and then later do another proof on the same committed witness, right? I'd have to like do the whole thing from scratch again. So you lose this like commit and prove property.
You mentioned these universal hash functions. Are they from like the lattices-based ones or the?
No, universal hash functions are just information theoretic objects that have been like studied since the 1970s. Yeah.
It's like generated from an MBS code or something like this, right?
So I am wondering the computational overhead compared to evaluation in the circuit in the clear, the computational overhead of the VOLE-in-the-Head.
So it depends a bit on the parameters you use. So I guess this tau parameter, which is kind of the number of repetitions in some sense, gives you a communication computation trade-off, right? So if you increase the parameter n, then you work a lot harder, but you get better soundness. So for instance, between this 10 and 16 bits per AND gate, there's maybe a factor 5 or 10 in computation.
But one thing to mention there is when you talk about evaluating the actual circuit, whichever way you do it, once you lift it to the large extension field, now you evaluate the circuit and like on them like max and everything, basically in the extension field. And this is an extension field of characteristic 2 usually for what Peter mentioned there. And in this case, you have like processor instructions that do that very efficiently for example, fields of size 128. So it's not that much more, it's not that inefficient in comparison to evaluating it in the clear over bits.
But yeah.
Thanks.
And for large finite fields like over 120-bit prime, then you have a much smaller constant because you're already working on like big field elements. You don't get that overhead. Okay, so I will now talk about an application of zero knowledge proofs. We haven't had so much of so far. And specifically an application which, as Carsten mentioned, is quite well suited to MPC-in-the-Head and VOLE-in-the-Head based proof systems, which is to building post-quantum signatures. So if you haven't been living under a rock for the last few years, you might have heard something about NIST and what they're doing with standardizing post-quantum signatures. So I think last year, the first round of standardization kind of ended with a few main candidates of signature schemes, which are 2 based on lattice-based assumptions, dilithium and Falcon, and then Sphinx, which is the hash-based signature. And these all have kind of different trade-offs and performance characteristics. The lattice-based ones are all very fast, and they have, I guess, compared with classical signatures, much larger signatures, but compared with other post-quantum signatures, still pretty small. Whereas hash-based signatures are, super nice from a security point of view. All you rely on is cryptographic hash functions. But the signing procedure for Sphinx Plus is really slow, and the signatures are also quite large, so 8 to 17 kilobytes for the 128-bit security level. So NIST, even though they're standardizing these things, they're still not fully satisfied with the possibilities here. They want things based on different assumptions, maybe with better performance characteristics. So they opened this new call for new signature algorithms to hopefully come up with a few more candidates to standardize. And this happened kind of by chance around the same time as we were developing the VOLE-in-the-Head proof system. So we decided to use this to build a digital signature scheme, a post-quantum signature scheme, where the only security assumptions we require are the hash functions and security of AES, standard block cipher. So this is kind of comparable to Sphinx, which is just based on hash functions, but we get much faster signing and smaller signatures at a cost of slightly slower verification with Sphinx. So I think we have a kind of a good compromise in the very conservative assumptions realm of post-quantum signatures. Okay, so how do you build signatures based on zero knowledge proofs? Well, there's this classic approach of taking a zero knowledge identification scheme and transforming it to a non-interactive proof, which gives you a signature, where one way of building the identification scheme is to take, say, some symmetric encryption scheme, encrypt a random message using a secret key, and then give out as a signature a non-interactive zero knowledge proof that I know the secret key corresponding to this message and ciphertext, which are part of the signature. So the only thing that's secret here is the secret key for the symmetric encryption. So then the question becomes, right, how do we instantiate this encryption scheme in a way that is kind of nice to prove in zero knowledge? So it doesn't have a really complicated circuit. It works well with good proof systems that we know. So in the past, there have been many based on custom block ciphers like Picnic, which used the low MC cipher, which was designed to be have a low circuit depth and be good for multi-party computation, zero knowledge. There are code-based signatures, which use syndrome decoding-like assumptions. And we thought, why not try to use AES? So AES was not designed for this purpose, but actually, I think it turns out to be, in some cases, a really zero knowledge friendly symmetric cipher. So let's have a quick recap of the structure of AES here. So it's this block cipher where encryption happens over many rounds. In each round, you have the linear layers, shift rows, mixed columns, and adding the round key, which are all linear over F2. And then the only nonlinear part is the S box, so substitution table. which actually happens to have a nice representation of the finite field f2 to the 8. So this looks like the kind of stuff which works quite well with MPC-in-the-Head and VOLE-based proof systems. So the high-level approach is that the prover will define this extended witness, which is going to be the AES key, together with the state of the encryption algorithm after every round. Right? So one block per round of the block cipher. And then we'll commit to these using vol and then prove the consistency of consecutive states for each round. Okay, so how do we do this? So linear parts of the round are kind of easy, right? We can just locally evaluate linear operations on commitments. So all we need to worry about is the S box, in fact, the nonlinear part of the S box, which is exactly this field inversion or like almost field inversion. So it takes an 8-bit input and maps it to the inverse in f2 to the 8, or 0 if the input was 0. So if we have two states for neighboring rounds, then we can define commitments to the input and the output of the S box, and we want to prove these are consistent. Well, why not just multiply them together and check we get one? So this works almost, except for the cases where X or Y is 0. So one way to work around this is actually to kind of cheat and say, okay, let's sample the secret key of AES and do rejection sampling such that we never get a 0 as an input to an S box. Turns out that this happens, not too often. I mean, not too infrequently. You can do it fairly efficiently. It reduces the size of the key space by maybe a couple of bits. So it seems not too bad heuristically. And then checking every S box reduces to checking one multiplication in f2 to the 8.
It doesn't depend on the message that is.
Right. Yes. So the message actually is part of the public key, so will never change. So when you generate the key pair, you pick the random message and you pick the secret key such that this holds.
Yes, that you only lose so few securities. So this holds over all the rounds, then you have over all option to each. It's never.
Yeah. So and it's about a 1 in 256 chance that you get a 0. There's about 200 S boxes and a 128-bit AES. It's not too bad. Okay, so that's actually the approach we took in the main signature scheme. There's also another approach you can do, which I'll talk about on the next slide. Is there a question?
Yeah, I mean, I guess we're gonna run multiple S boxes. So what if one of them is 0? Then you have to rerun the first X box, such as the whole chain.
So then, if one of them is 0, then we just resample the keys and start key generation again.
Okay.
This all happens at key generation. Then the message and the key are fixed. So every time you sign, you're just running a proof for the same statement. Thanks. Yeah. So there's an alternative approach which avoids this non-zero S box issue, but is also a little bit more heavy-handed. But I think it's a nice example of this high degree kind of polynomial relations that I mentioned that you can do in vol-based zero knowledge. So instead of just proving degree 2 relations, you can prove higher degree relations on committed values by letting the degree of these polynomials blow up as you multiply them together. Okay, so now let's look at 2 consecutive rounds of AES. And for each round, we have, let's say, a state xi, which goes through an S box, and to get some value yi, and then which goes through the linear part of the round to get the next state xi plus 1. Okay, so if we actually look at the S box as a Boolean function, then it turns out this has degree 7 over f2. It's not too hard to see if you just look at the field inversion formula as an exponentiation and work out the addition chain. Degree is not too high. So if you imagine we have, say, commitments to xi using our vol-based commitments. So these are degree 1 polynomials using defined using the vol output of Alice. And then we can basically evaluate the Boolean circuit that computes the S box on these polynomials. And we end up with at most a degree 7 polynomial at the end. Okay, so then you can say, okay, so now I can check xi is consistent with yi, the degree 7 check. And that's very nice, but actually I can do even better. Now I can verify 2 S boxes at once. So I can check xi is consistent with xi plus 2 by doing a meet in the middle approach. So I evaluate the nonlinear part on xi, followed by the linear layer, and I evaluate the inverse on xi plus 2, and then you get the same thing in the middle. These are 2 degree 7 polynomials. You just add them together, check you get 0, and this is a kind of degree 7 polynomial check in the VOLE proof system. So the effect of this is that we've halved the witness size, right? So now instead of committing to the state at every round, you just commit to it at every other round. The price you're paying for this, of course, is you have to work with these up to degree 7 polynomials. And when you do this kind of check at the end, even though it's a batch check of just a single set of polynomials, it's quite a bit larger than the degree 2 ones. And you pay some more for that. You need some extra masking values to make sure you're not leaking anything. So there's a bit of a trade-off, but if you work it out, you can get smaller signatures by roughly 5 to 10%. It's a small improvement, but it's something nice compared with some of the original variants of the FAEST scheme that we proposed. So yeah, I guess this is kind of the summary of the proof system together with how it's used for FAEST. I think we can skip that. I'll just talk a little bit about performance. So I have some numbers here for the original submission that we made to NIST last year. These have been improved a bit using the GGM tree optimizations that Carsten mentioned and some other tricks which can get the runtimes around 10 to 20% faster. Sorry, the sizes around 10 to 20% faster. And the signature size is around 5 kilobytes for the smallest and slowest version, 128-bit security level. And then you see if you move to the faster but larger version, which is basically increasing the number of repetitions, the size of cost of reducing this n parameter, so the soundness is worse, then the computational cost increases by about a factor 10. So there's a pretty heavy computation trade-off to get these 1 kilobyte or so reduction in signature size.
So what's the S and the F?
This is just what we call short and fast for the different versions. Yeah. And then the 256-bit security level using AES 256, I guess, is around, you get the twice the security, you pay around a factor 4 in signature sizes and runtime, which is a bit annoying, but that's how it is. Yeah, so I guess I finished pretty early. So we have plenty of time for more questions, but I'll maybe just wrap up and then get back to that. So we've seen VOLE-zk proof systems, both in the designated verify setting, using some kind of ideal vector OLE functionality. And these offer a kind of nice, clean information theoretic approach to building zero knowledge that can also be very efficient, have some nice properties in various settings. And now we've just seen how to make these publicly verifiable using these GTM tree-like approaches and some special conversion routine based on MPC-in-the-Head. I can use this to build actually pretty small and fast post-quantum signatures based on very conservative security assumptions. And I'm hoping that that's just one application of many other things which people will find to do with these VOLE-in-the-Head based proofs.